Alright, so this time we're doing problem 53 from chapter 6, and the problem says, a luggage handler pulls a 20 kilogram suitcase up a ramp inclined at 32 degrees above the horizon by a force with a magnitude of 160 newtons that acts parallel to the ramp. The coefficient of kinetic friction between the ramp and the inclined plane is mu is equal to 0.300. If the suitcase travels 3.8 meters along the ramp, calculate A, the work done on the suitcase by the force, B, the work done on the suitcase by the gravitational force, C, the work done on the suitcase by the normal force, and D, the work done on the suitcase by the frictional force. Then E asks, what is the total work done on the suitcase? And then finally, F, if the speed of the suitcase is 0 at the bottom of the ramp, what is its speed after it has traveled 3.8 meters along the ramp? So, for A, we're looking for the work done by the force of the man pulling the suitcase up the ramp. So it's this force that the worker is applying. We know that the work is going to be equal to the integral over the distance time of the force times dx. So we know that it's initially starting at 0 and it's going to 3.8 meters. So those are the bounds on the integral. The force is going to be equal to 160 newtons times cosine of the angle. And in this instance, because it's the angle between the direction that the force is applied and the direction that the object is moving, and since the force is applied in the direction that the object is moving, the angle is 0 degrees times dx. So all of this can get pulled out of the integral. So that then becomes 160 cosine of 0 integral dx from 0 to 3.8. So that just becomes 160 times cosine of 0 times 3.8, because 3.8 minus 0 is still 0. And that's going to be times all of those. And when you work that out, you get that the work done by the force is 608 joules. So then part B wants to know the work done by the gravitational force on the suitcase. So, we know that the work of gravity is going to be equal to the integral of the force over the distance, x1, x2, and then because gravity works on the center of mass down, the component of the gravitational force that's going to be acting in the direction of the inclined plane is going to be sine of the angle of the ramp. So we're going to have the mass times the gravity times sine of the angle dx. So then all of that comes out of the integral. So we get mass times the gravity times sine the angle integral dx from x1 to x2. Then you just plug in your variables. So the mass of the suitcase is 20 kilograms times 9.81 times sine 32 degrees times 0, or 3.8 minus 0 is still 3.8. So that's 3.8. And then when you do the math, that comes out to 395 joules. But gravity is going to be working opposite the direction that the suitcase is traveling, so that's going to be negative work. And so that's your answer for part B. For part C, it wants to know the work done by the normal force. So we know that the work is going to be equal to the integral of the force times the cosine of the angle dx. But in this instance, the angle is going to be 90 degrees, and cosine of 90 degrees is 0, so the whole thing is 0. So the work of the normal force is going to be equal to 0. Then part D asks for the work done by the frictional force. So we know that the work of friction is going to be equal to the integral x1 to x2 over the force. The force is going to be the kinetic coefficient of kinetic friction times mass times gravity. Mass times gravity. Just a second to look at my notes for this one. Yeah. Times cosine of the angle dx. And it's cosine because not all of the weight is working down, because the weight vector is going to go straight down 90 degrees from the horizon. But we're only interested in the y component of that weight. And so it's cosine of the angle of the ramp, because that'll give us the y component of the mass vector, the weight vector, or the weight force. So then all of these are constants with respect to x, and so they can come out of the integral. So the work of friction is going to be equal to mu times m times g times cosine of the angle, and then you would have x2 minus x1, but x1 is 0, it goes to 0, so that's taken out, and we plug everything in. Coefficient of kinetic friction is 0.3 times 20 for the weight of the suitcase, or sorry, not the weight, the mass, times 9.81 times cosine of 32 degrees. Degrees times the distance traveled, 3.8 meters. So then when you do the work, do the math, to find the work, you get that the work of friction is going to be negative 189.7 joules. And it's negative because, like gravity, the work of friction is going to be opposite the direction that the object's moving. So then part E wants us to find the work total, which is just going to be equal to the work of the force plus the work of gravity plus the work on the normal force plus the work of friction. This one is 0, and we found all the others, so 680 minus 395, and then minus 189.7. When you do the math, you find that the total work done on the suitcase is 23.3 joules. So that's how much work is done to move the suitcase 3.8 meters up the ramp. Then part F asks, if the speed of the suitcase is initially 0 at the bottom, so our velocity initial is equal to 0 meters per second, what is the velocity when it's traveled 3.8 meters up the ramp? So, to solve that one, we know, so for F, part F, we know that the work is going to be equal to 1/2 mass times the velocity, the second velocity squared, minus 1/2 mass times the initial velocity squared. We know that the initial velocity is 0, so this term all goes to 0. We know the mass and the weight, and we're solving for the velocity. So we can rewrite that as the velocity is going to be equal to the square root of 2 times the work divided by the mass, which is then going to be equal to the square root of 2 times 23.3 divided by 20. And when you work that out, you find that the final velocity after the suitcase has traveled 6.8 or 3.8 meters is 1.5 meters per second. So what we did was we found the work done by all the different forces acting on the suitcase to find the total work in part E, and then we used the total work to find the final velocity of the suitcase after it had gone so far up the ramp.